Hello and welcome back to our next episode. We have Krishna back with us. Hello, Mr. Krishna.
Hello, Deepu. How are you?
I'm good, sir. How are you?
Yeah, good.
So it's been a while since we had a conversation. In the previous episode, we had mentioned about your IOA presentation, right? Post that you were away for quite a good time.
Yes.
So how did everything go, and what was the topic that you presented there?
Yes, that was a good international conference that covers a lot subject of predominantly acoustics, but good amount of vibration as well. Maybe my paper and two of others were quite close to the vibration related engineering consulting.
So what was the topic that you took in?
I took up one of the cases that we handle here, which is looks like a simple one, like field balancing of a complex rotating equipment, more connected to process industry. And the intricacies around it, because we are handling, or the project is about a variable drive with a fluid coupling as an interface, which is a challenging task to conduct both vibration analysis and balancing.
Okay. So can you give a quick briefing on what it was all about?
Of the subject itself, see, this process industry, in particular the steel industry that I'm referring to, uses large conveyor belts to transport the ore and the fuel material to the furnace. And these have very large motors in configuration, like 4 of them together, driving the single belt. 3 of them will be in operation, 1 will be on a standby. And because of this large load, there is both load, varying load, which means the torque and the load conditions are all the time changing. So to mechanically handle this, one of the good ways is to use a coupling. And out of this many couplings available, one of the most practically usable coupling is called a fluid coupling, which is nothing but a hydraulic coupling by itself. For anybody who do not know much about this type of coupling, there is really no physical connection between the input and output of such a coupling. An oil is the medium there, and as soon as the input side, imagine the motor driving it, the fluid inside this coupler starts spinning, and then it attains a critical speed of centrifugal force. And after a while, this oil gets coupled as a mechanical coupling, and then starts driving the output. So as you can see, oil is the connection. So oil doesn't wear or do anything. There's no mechanical wear and tear. And then it transfers the force or the rotational drive to the output, thereby handling both the slip, the torque and the varying loads very effectively. And that is that is the case that we are handling.
So where does balancing come into picture here?
So now I told you this arrangement. There is a large 3.3 megawatt motor, and then there is a coupling in between which statically weighs about 650 kilos, and with a fluid fill of about 70 liters of special grade oil, and then connected to a gearbox and the belt line. So what is the necessity of balancing? 2 things. Any rotating equipment, for example, will have some residual unbalance, even though they are balanced as they are manufactured, component by component. But once they are put into an assembly, here we are talking of a large motor, its output coupling, then there is a gear coupling, then there is this fluid coupling, then there is the output gear. So there are so many rotating parts connected to. It is obvious that there will be some residual unbalance. And this residual unbalance, because of the sheer size of the coupling itself, can generate a good amount of centrifugal force and the related vibration. So this calls for the balancing activity at site, even though the manufacturer or supplier says this is well balanced to some ISO grade. Now the complexity comes because 1 is the assembly, the maintenance quality of all our practices that we have. 2 is also because this is a variable speed drive. So you never know, maybe it may be apt somewhere through the conversation to handle that. But if you leave this unbalance, and if that happens to be in a very critical zone of it, this is going to create a lot of vibrations, thereby lowering the overall life and the operability of the system.
So let's say a system is undergoing some kind of unbalance. Do you believe that 50% of the issue or the vibration issue is because of this unbalance?
On a statistical, the data available from many of machine tool background, 50 or even more vibration related problems investigated in any rotating equipment is because of unbalance. This is proven. And this is also proven through our consulting experience of 20-year plus, that you start, but you can't take it as a kind of pre-qualifier that this is the problem, but most of it, 50-60% of it is contributed by unbalance. This is known.
So since the load is acting on the bearing, what kind of effect can this happen? Can the bearing actually face?
Oh, you mean the unbalance related load?
Exactly.
Yeah. So any load, finally bearing by name, is the one to take all the loads. And it's the interface between the rotating and the static member, which is the housing to the rotating part. Includes your unbalance, that is the interface where all the forces are transferred. Why we typically and more significantly look at unbalance is this is one great value of force which is rotating as a function of 1 into RPM and has a direction which is directly on the bearing. So even looking to large bearings that support these kind of rotating equipment, a continued load of centrifugal force with a large amount of force is sure to deplete the quality of bearing and overall end up in a lowering of the life itself.
You mentioned about critical speed, right? Let's say a system is undergoing unbalance and it's operating somewhere close to a critical speed. Then what kind of failures can it have?
That is something that we see everywhere where we go for. So first is a quick understanding of what is critical speed. All that we talk of rigid rotor by concept, I'm not going into the theory, till it is passing through. I mean, we know that force is proportional to, or vibration is proportional to the force that's being generated. But once the system is closer to its first flexible mode, which is typically called a critical speed in rotating equipment, also we call in static equipment as natural frequency or one other. So now you see that the operating frequency is trying to coincide with the natural frequency of that rotor or the rotating part.
Okay.
Now you have a problem because your excitation frequency and your response frequency will add up, and this is going to again kind of unproportionately increase the vibration depending on damping forces and other things in the system. This is a almost dangerous condition that we are talking of. And to identify, just to continue with that, to identify a critical speed in a machine, you do a discrete speed or you do a run up or you see where is that happening. Try to avoid that speed when you conduct balancing, which is very, very important. And try to do balancing prior to that first critical speed. Don't cross the critical speed. Do it when it is in the rigid mode. And then once you are done with attempting a lot of correction, you can cross that speed. You obviously will see a lot of it.
So when should engineers actually choose in-situ balancing or the machine-based balancing?
So machine-based balancing is in the factory stage. When the individual parts are made, their rotating residual unbalance are to be identified. There is a ready-made machine on which you mount the rotor part, drive it with some a prime mover, do the balancing as per the standards. But when all these parts are made and again put together, there may be less provision to put this again on that machine. So this becomes a case for in-situ balancing. Many a times, a good quality individual component made may not require when it is assembled, but there are cases where you put them all together, like the case that we are talking now, will end up in a requirement of in-situ balancing. That's the engineering judgment you have to make.
Understood.
Yeah.
Thank you, Mr. Krishna. So I think we can wrap it for today. Hope our viewers found it interesting. We'll catch you all in the next episode.
Thank you very much. Thank you.